Okay. So moving to the Rayleigh method, it is also called RR method. So here what happens for any continuum, the total strain energy can be used to find out the approximate solution. Just now we have seen the previous problem. So RR method uses this uh, Rayleigh method. RR method is nothing but this Rayleigh method uses the potential energy method to get the solution to the problem. Where if it is a simple problem, I will get the I will be knowing the exact displacement through the MOM approach. But whereas for some uh, complex problems, now there in that case I will be not knowing what is the displacement using MOM approach, or it is very difficult to know what is the displacement using MOM approach. So in that case, this Rayleigh method uses this potential energy to get the solution to the problem. Now, Rayleigh and Ritz, these are the two different persons. They have formulated this concept where Rayleigh has given the uh, what the coordinate general coordinate system, whereas Ritz has given you the trial function. So altogether, the function will look like this, where u is equal to summation of ci into pi I, where ci is the general coordinates and pi I is what it is the trial function. Now you already know when I consider the displacement function, either I can go with the polynomial function or I can go with the trigonometric function. So if I consider polynomial function, my displacement will be u, that u will be equal to, it is a naught plus a1x plus a2x square plus a3x cube plus and so on. So this is my uh, a displacement function in the form of a polynomial function. So if I consider here a naught, a1, a2, a3 are nothing but my general coordinates, whereas x, x square, x cube are treated as a trial function. Okay, so this generalized coordinates that is given by Rayleigh, and trial function is considered by the Ritz. So altogether, this what we call it as a Rayleigh's method. This is in case of polynomial function. If I consider a trigonometric function, I have c1 into sine pi x by L plus c2 into sine 3 pi x by L. So like this plus so on. Here C1, C2, C3 are what we taken it as a generalized coordinates, and whereas sine pi x by L, sine 3 pi x by L, then next term will be sine 5 pi x by L. So these terms we are taken it as a trial function. So both, either you consider a polynomial function or a trigonometric function, it consists of a generalized coordinates as well as a trial function. Okay, so this is what the concept of Rayleigh's method. So there are some steps in the Rayleigh's method. So these are the steps in the Rayleigh's method. First, you need to formulate the P function of a given body or given continuum. Then after formulating the P function, next what you need to do, you have to assume a trial displacement function for that whatever the continuum you have considered. And one more condition is whatever the trial displacement function you are considering, it should assume, it should satisfy the given boundary condition for that particular problem. Then third is after assuming and satisfying the boundary condition, that displacement function I have to substitute in this P function, what you have formulated for the particular body. Once you have substituted the displacement function into P function, then I need to minimize that P function to get the equilibrium condition, or you need to get the equations. When you solve those equations, I can get the displacement. Once if I get the displacement, I can calculate the stress and strain for that particular body. So this is the 5 steps which consist of this RR method. I'll quickly repeat. First, I need to formulate the P function. You know how to formulate the P function. The P function is denoted by pi. How to formulate? It is a strain energy plus work potential. So this formulation I have to do. Once this is done, I have to assume a trial displacement function, and this trial displacement function should satisfy the given boundary condition for that particular problem. Once this is done, that trial displacement function I am substituting in this P function. Once it is substituted, then I need to minimize. How to minimize? I need to differentiate that P function with respect to unknown. Any unknown. Let us consider if X is the unknown. So I need to differentiate that P function with respect to that unknown, and I need to equate it to 0. That is what minimizing the P function to get the equation. Then finally you solve those equations. If there are two unknowns, I will be having two equations. If I am having three unknowns, I will be three equations. By solving those three or two equations, I am going to get those unknowns. And finally, those unknowns usually in the form of displacement. Once displacement obtained, your stress and strain can be calculated. So these are the simple 5 steps used in RR method. Okay. So directly we'll start the problem here. We have problem on bars and we have problem on beams using the same RR method. So let us begin with the bars first, and once all the problems related to bar, if it is completed, I'll go to the beams. So let us begin with the simple problem. Find an expression for the displacement in the system shown in the figure below. I'll draw the diagram for using RR method. So it is a simple uniform bar. It is a simple uniform bar fixed at one end. And it is applied with an axial force P. And this is having this bar is having an Young's modulus E and cross sectional area A. See, whatever the problems I am solving here, all it is in the form of expression. If values are given, you can substitute the values finally after getting the expression. So this is the bar which is having a length L, having an Young's modulus E, having some particular material, and area A subjected to an axial force P. Now I have to find out the expression for displacement. Can you tell me what is the expression for this? A uniform bar subjected to point force, how to find out the displacement or extension? Because of this applied force, let us consider this is the extension in the bar, and this extension in the bar, let us consider it as a delta L. How to find this delta L? That is what my question. See, you know stress will be equal to force by area, strain will be equal to delta L by L. So from Hooke's law, stress will be equal to Young's modulus into strain. So stress is force by area, Young's modulus as it is. What is strain? Strain is delta L by L. Therefore, delta L is equal to, so this L I will send it to the LHS, so it will be PL. This E I will send it to the LHS, therefore it is AE. So what is the expression?
PL by A.
This you already studied, no? How to find out the extension in uniform bar is given by PL divided by AE. So this is my expression to find out the extension in the uniform bar, PL divided by AE. This you know in using MOM approach. But same thing I have to do with RR method, and I need to check whether I will get the same expression or any different expression. That will check it. Okay. So begin with the first step. What is first step? Formulate the P functional. So how to formulate? It is pi is equal to is strain energy plus work potential. Correct, no? So first I need to find out the expression for strain energy, and then I need to find out the expression for work potential. Substitute those two here, I'll get the total P function. That is my first step. So first I'll find out the strain energy. Now what I will do? Let us find out the strain energy for a small element here. Then I'll put the integration to find out the strain energy in the total length of the bar. So if I consider strain energy for the element, how to find out the strain energy for the element? It is a uniform bar, it's a bar. So strain energy in the bar is given by what? It is half into stress into strain into volume. So let us consider this element is having a length dx and area is same A. So half into stress into strain into volume. Volume is what? Area into length. Length of the element is dx because I am doing for the element. Now if I want to find out the total strain energy, it is integration over the length of bar, half into stress into strain into area into dx. So this will be equal to 1 by 2. I'll take it outside the integration. That is integration over the length of the bar, stress, strain, area into dx. Say strain energy in the bar is different, beam is different. So strain energy in the bar is given by half into stress into strain into volume. So as I am doing for the element, I have considered volume of the element. This is my entire volume of the element, that is area into length of the element, where length of the element I have considered it as an dx. Then if I want to know what is the total strain energy which is there in this bar, so I need to consider such small elements and I need to assemble those elements. Therefore, I put the summation, that is nothing but integration over this entire length of the bar L. So half into stress into strain into volume. Therefore, I will get the total strain energy where 1 by 2 I have taken outside. Now, here I need to try to represent this strain energy expression in terms of strain. So what I am going to do here is, so you strike out this, it is not there. Now, my strain energy is equal to 1 by 2 as it is, integration. I have stress. So stress I can write it as Young's modulus into strain from Hooke's law. Then strain as it is, area into dx as it is. So in this previous expression, this stress from Hooke's law I am substituted as Young's modulus into strain because stress is equal to Young's modulus into strain. This strain as it is and area into length of the element as it is over the length L. Now further simplification I will do it. So strain energy will be equal to, it is half over the length of the element. This epsilon, it will become epsilon square. Then EA into dx. Okay, so epsilon into epsilon, epsilon square. This E into A as it is, this dx as it is. So EA, it is material constant. So this also I'll take it outside in the next step. Therefore, strain energy will be equal to, it is EA divided by 2 integration over the length of the element epsilon square into dx. Okay, because this epsilon, that is strain, it is in terms of displacement, it is with respect to the length. Therefore, this cannot be taken outside. Now, this strain can be written as du by dx. That is differentiating the displacement with respect to the direction will give you the strain. So this epsilon can be written as du by dx. So let us substitute du by dx here. Therefore, my strain energy will be equal to, it is EA divided by 2 integration over the length. It is du by dx whole square into dx. Okay. So this is my entire strain energy. So this I'll take it as an equation number 1. So if I write directly this equation, you will be in confusion. Therefore, I have shown you how strain energy you will get it in the form of this equation. So any bar problem, this is the strain energy which is fixed. So in the examination, you cannot do all these steps. Directly you can write this equation. So initially if I write, you will be in confusion. Therefore, I have reduced and I came to this. Okay. Now next is I need to find out the work potential. So work potential is force into uh, extension. So it is P is the applied force. So extension, let us consider it as an U1. Say instead of this delta L, now here I am going to consider it as an U1. So applied force is here and extension in this portion is U1 I have considered. So it is P into U1 is my work potential, nothing but it is force into displacement. And it is negative sign because the force is acting upon the system. Now this is my second equation. So this is my first equation, strain energy. This is my second equation, work potential. Therefore, now P function pi is equal to, it is strain energy plus work potential. So therefore, pi is equal to strain energy is EA divided by 2 integration length 0 to L. I am going to consider the length as 0 to L. Here I have du by dx whole square into dx minus P into U1. This is my entire P function. This is my first step in RR method, formulating the PE function. So this much you need to formulate. But only thing is, I have started with this strain energy equation. Then I have reduced to a final equation of strain energy. Work potential is nothing but it is force into displacement. So that I have considered directly. So that is my first step, formulating the PE function. So I have formulated the PE function. What is my second step in the RR method? Yes. I have to consider the trial displacement function. So I am using a word trial here. Therefore, I don't know up to what order I have to consider. You need to assume it trial. As a trial and error. If you are not getting the desired equation, you have to increase the number of uh, uh, terms there. So let us consider with a naught a1x plus a2x square. So this is the u is equal to this is the polynomial function I am going to assume here as my displacement function up to second order. I am going to assume up to second order, that is a2 into x square. If I am not getting the desired equation, then I have to increase one more step here, that is plus a3 into x cube. Okay, so let us go with up to second order. Usually up to second order you will get the desired equation. If it is not so, you have to increase the one more step. Now in the second step, after assuming a trial displacement function, what he has mentioned, this trial displacement function should satisfy the given boundary condition. Now what is that given boundary condition? When x is equal to 0, when x is equal to 0, what is the displacement? U is equal to, so I am considering U as a displacement, because what is the boundary condition here? See, here my x is equal to 0, and at this end my x will reaches L, that is length of the bar. So when x is equal to 0, as it is fixed here, there is no displacement, therefore my U is equal to 0. When x reaches L, my U will be equal to U1. So this is the displacement which is there in the free end. So my displacement will become U1 when x is equal to L. My displacement will be 0 when x is equal to 0. So that is the boundary condition I am substituting here. So when x is equal to 0, U is equal to 0. So in this above equation, wherever x is there, you put 0, and wherever U is there, you put 0. So 0 is equal to, because U is here, so U is 0. A naught as it is, plus A1 into x is 0, plus A2 into x is 0. Therefore, this A naught, A1 into 0 is 0, A2 into 0 is 0. Therefore, what I'll get the value for A naught. So value for A naught is 0. So one constant I obtained here, that is A naught is equal to 0 by substituting the first boundary condition, that is when x is equal to 0, U is equal to 0. Similarly, I have to go with the second boundary condition. What is my second boundary condition? When x is equal to L, U is equal to U1. When x is equal to L, U is equal to U1. Therefore, in this displacement function, wherever U, I have to replace with U1, and wherever x, I need to replace with L. So I'll do that. So U is replaces with U1. This will be equal to, see, A naught in the previous step you obtained, it is 0. So I'll put 0 plus A1 into x. X is nothing but L. I need to replace x with L, plus A2 into L square. X square now replaces with L, therefore it is L square. Therefore, my U1 will be equal to, it is A1 into L plus A2 into L square. So this is the equation I am getting for U1. So if at all I want to find out what is the expression for U1, I have to find out this constant A1 and A2. By substituting the constant value A1 and A2, I will get the value of U1, and that value of U1 should be equal to PL divided by AE. Correct? No? Because here I have considered U1 is equal to delta L. Whatever this extension, in the MOM we are going to consider it as a delta L, but here in the FEM I am going to consider it as a U1. So my delta L is what? It is PL divided by AE. Therefore, my U1 should be also equal to PL divided by AE. So we'll check that. by substituting the value of a1 and a2, whether I'll get the same equation or not. That will check it. Now, for example, if when x is equal to x, what is x is equal to x? Means at any random distance. Let us consider this is my distance of x. Any random distance, if I want to find out the value, then u will become u. So this is the expression for any random distance. This is the expression for at the free end, and this is the expression where it is fixed end. And any random distance, if I consider, it is u is equal to a1 into x plus a2 into x square. This is the expression of u at any random distance, where I need to find out once again a1 and a2. By substituting a1 and a2, I'll get the value of u, and this value of u will be at any random distance. Okay, so this is the getting the assuming the trial displacement function and satisfying the boundary condition. Now, what is my third step? After satisfying the boundary condition, I need to substitute this displacement function. Substitute this displacement function in PE function. Okay, so what is that? How I have to substitute? Phi is equal to, it is EA divided by 2 integration 0 to L d by dx of u, means it is du by dx. What is my u? U is this. Let us substitute u as a1 into x plus a2 into x square. Then this entire term whole square into dx minus p into u1, where u1 is what? u1 is a1 into L plus a2 into L square. This is the value of u1 that I am substituting here. P as it is in the PA function, this P as it is, see this P as it is, u1 is replaces with this expression. u1 is replaces with this expression that I have substituted here. So that is what substituting the displacement function into PA function. So this substitution I have done. Further I will do the simplification, then we can go with the fourth step, that is minimizing the PA function. Actually, we are interested in this maximum displacement, but sometimes what happens, if you want to know what is the displacement at any random distance in the bar, that equation also you can get it. That is what, when x is equal to x, u is equal to u. So a0 is 0, therefore u is equal to a1 into x plus a2 into x square. This is the expression for any random distance. This is the expression for any random distance in the bar. Expression for displacement at any random distance. That means to get that displacement u or u1, to get the displacement u at any random distance or u1 at the free end, I need the value of a1 and a2. I need the value of a1 and a2. These are the two constant value I have to get. So to get these two constant values, I need to minimize the PE function. Okay, further is what I need to do the simplification. Now what I will do, first I will differentiate this with respect to x, then whatever the value I am getting, that I will square it. Okay, so I will do that. So in the next step, it is d by dx of a1 into x plus a2 into x square. So this I need to differentiate. If I differentiate, what I am going to get? a1 constant, differentiation of x is 1, plus a2 as it is, the differentiation of x square is 2a2x. Therefore, it is a1 plus a2 into 2x, that I have written as 2a2x. Okay. So this value I need to substitute in that p function. So pi is equal to, outside I have ea divided by 2 integration 0 to L. What is that? It is a1 plus 2a2x whole square into dx minus, now what I have p into this term. So let us take this p inside the bracket. If I take p inside the bracket, what I am going to get? It is p a1l plus p a2l square. Okay, I'll put the bracket here, negative sign I have taken outside. So when I take that p inside, here it is p into a1 into l plus p into a2 into l square. So same thing I have written, p into a2 into l square. Okay. Now this I have to expand with a plus b whole square. Then I have to integrate it. Okay. So I'll expand that a plus b whole square first. Then I'll do the integration. So it is a divided by 2 integration 0 to L. It is a1 square plus 2a2x whole square my plus 2ab. This is my 2, this is my a, this is my b. Correct now? Is it correct? Then this dx as it is, then this negative sign I'll take it inside. So it is minus p into a1 into L minus p into a2 into L square. Okay. Now further I'll do the simplification. So pi is equal to, it is EA divided by 2 integration 0 to L. So let us expand it once again. It is a1 square plus this square I'll apply here. It is 4 a2 square x square plus 2 into 2 4 a1 a2 x. So 2 into 2 it is 4. This a1 as it is, this a2 as it is, this x as it is, into this dx as it is, minus p into a1 into L minus p into a2 into L square. Therefore pi is equal to, now I'll integrate this entire term, I'll integrate with respect to x. Okay, and I'll put the limit 0 to L, upper limit minus lower limit, I'll do it. Okay, so a1 square as it is into x, differentiation of constant with respect to is x, plus 4 a2 square as it is, integration of x square is x cube by 3, plus 4 a1 into a2 as it is, integration of x is x square by 2. Put the limit 0 to L. Then this is a term as it is, p into a1 into L minus p into a2 into L square as it is. Now you have to, here I have to do upper limit minus lower limit. See here, all these three terms consisting of x. Here I have x, here I have x, and here also I have x. Lower limit, when I substitute x as 0, means my lower limit term, when I substitute 0, this entire term will become 0. Only I have a value for L in the upper limit. Therefore, let us show only substitution of upper limit. I'll not show the substitution of the lower limit, because my lower limit is 0 and all the terms are consisting of x. Therefore, it is a1 square into L plus 4 a2 square, it is L cube by 3, plus 4 a1 into a2 into L square by 2. Lower limit is 0, that I am not showing. Then minus p into a1 into L minus p into a2 into L square as it is. These two terms I'll keep it as it is. Okay, now fourth step in Rayleigh-Ritz method, fourth step is to minimize. So minimize p, I have to differentiate that pi with respect to a1 and equate it to 0. And the same p function I have to differentiate with respect to a2 and equate it to 0, because I have two unknowns here, a1 and a2. a1 and a2, everywhere I have a1 and a2. So I have to differentiate that p function with respect to a1 equated to 0, I'll get one equilibrium equation. Similarly, same equation, p equation, when I differentiate with respect to a2 equated to 0, I'll get second equilibrium equation. Solve those two equations to get the values of a1 and a2. Because why I am getting this value of a1, a2? Because to get this u1, that is my maximum displacement which is there at the free end, it requires the value of a1 and a2. Constant values, a1 and a2 values are required. When I substitute, I'll get the final equation u1. Therefore, I am minimizing that p function with respect to a1 and a2. Okay. Now let us do it. First one, that is, I am differentiating that p function with respect to a1. So when I differentiate this ea by 2 constant as it is, a1 square into L is nothing but 2a1 into L. So outside I have ea divided by 2 as it is. It is 2a1 into L plus, see, here I don't have any a1 term. Therefore, this entire term will become constant 0. Here I have A1. So differentiating this entire term with respect to A1 is 1. Remaining constant terms are 4A2 L square by 2. So that I am writing 4A2 L square by 2. Then minus differentiation with respect to A1 is 1, is the remaining term is PL, and this is A2 constant term, so this will become 0. Therefore, it is minus PL equated to 0. So this is let us say equation number 4. Previously I left at equation number 3. No, this is my equation number 3. Or what you can do is this, you can do it equation number 4, and this you can do it equation number 5. Okay, so this is my equation number 5. Equation number 4 is the required displacement equation. Okay, U1 is the required displacement equation, that I'll give the equation number 4, and this I'll give it as equation number 5. Similarly, the same P function I have to differentiate with respect to A2 and equate it to 0. Okay, so first I'll differentiate, then I'll equate it to 0. So outside I have EA divided by 2 as it is, constant term. Then see here, when I differentiating with respect to A2, now A1 term will become constant, this is 0. Then here 4L cube by 3 constant, the differentiation of A2 square is 2A2. So 2A2 into 4 is 8A2. So that I'll write down 8A2 L cube by 3. Okay. So directly I am substituting the simplified value here. It is 8A2 L cube by 3 plus here once again A2, I need to differentiate with respect to A2. Therefore, constant terms are 4A1 L square by 2. So that I'll keep it as it is. 4 A1 L square by 2. Then this is A1 constant 0. With respect to A2, when I do, it is minus P into L square. So it is minus P into L square is equal to 0. So let us take this as an equation number 6. Only thing is now I have two equations. I have two unknowns, A1 and A2. Therefore, you solve these two equations as a simultaneous equations to get the value of A1 and A2. Once if you get the value of A1 and A2, substitute in that U1 equation, so that you will get the expression for displacement, maximum displacement. We are always trying to get the expression for maximum displacement, so that you will get that maximum displacement. Now, next is only thing I need to do the simplification to solve these equation number 5 and 6. So before solving, let us do some of the simplification here. So what I can do is I can take this EA divided by 2 inside the bracket. I will take this EA divided by 2 inside the bracket. So this 2 will be get cancelled. So what I will get, EA A1 L. Similarly, when I take this EA to this term, this is plus. See here, this 2 it is 4. Therefore, this 4 will be get cancelled. I'll be left out with EA A2 L square minus PL is equal to 0. Just I simplified by taking this EA divided by 2 inside the bracket. Similarly, this EA you can take it inside the bracket. So what I am going to get? This is 2, this is 4. Correct now? So it is 4 EA 4 A2 L cube by 3. So it is EA A2 L cube 4 by 3. I'll keep it outside. Is it correct? 4 by 3 EA A2 L cube. Similarly, when I take this EA by 2 inside the bracket, so this 2 it is 4. That 4 will be get cancelled with this 4. Therefore, it is plus EA A2 L square minus P into L square as it is equated to 0. So just I simplified and obtained these two equations. Now I need to solve these two as a simultaneous equation. Now, sorry, this is A1 now. I'll change it. So here, this is not A2. When I take this A multiplied here, I have A1 here. So this is my A1. So I'll change it. So this is my A1. Okay. A2 is here. This is A1. Now if I want to solve these two equations as a simultaneous equation, now here I have EA A1L and here I have EA A1L square. So some of the terms I have to cancel, but thing is here I have single L, here I have L square. Therefore, what I will try to do, I'll try to multiply the first equation throughout L so that some of the terms will be get cancelled. So that I'll do it here. It is E A A1 L square. So this L into L, it will become L square plus E A A2 L cube, because L square is there, multiplied with L, it will become L cube minus P into L square. So L is there, multiplied with L, it will become L square is equal to 0. So second, I'll keep it as it is. Only I'll just rearrange the terms. This EA A1L, I'll take it first term so that it will become easier for the cancellation. So it is EA A1L square plus 4 by 3. This term I'll take it next. 4 by 3 EA A2 L cube minus PL square is equal to 0. So this PL square I'll keep it as it is. Now you solve these two as a simultaneous equation by changing the sign. So I have positive here, so therefore I need to change it to negative. This is positive, I need to change it to negative. This is negative, I need to change it to positive. So EA A1L square, EA A1L square, one positive, one negative will be get cancelled. Then here minus PL square, this is plus PL square. These two are also get cancelled. Then what is left out? I have EA A2 L cube is first term. Now I have changed the sign here, so it is minus 4 by 3 EA A2 L cube is equal to 0. Is equal to, I have 0 here, so is equal to 0. Then can you tell me what is the value of A2? What is the value of A2? See, if I take A2 common from these two terms, if I take A2 common from these two terms, whatever the term I am going to get it here, when I send it to this side, 0 upon anything, it will become 0. Therefore, my value of A2 is equal to 0. In these two terms, if I take A2 common, what is left out? EA L cube minus 4 by 3 EA L cube. If that term, when I send it to this side, 0 upon anything, it will become 0. Therefore, my value of A2 is equal to 0. Now, one value of A2 I obtained 0. Then I need to substitute this value of A2 in any one of the equation here to get the value of A1. So that I am doing here. So let us substitute in this first equation. So it is EA A1L square. So EA A1L square. Then plus EA A2, A2 is 0. See, I have second term is EA A2, A2 is 0, L cube minus PL square, P into L square is equal to 0. I have substituted the value of A2 in this equation. So this entire equation is 0 multiplied by 0. This entire equation is 0. This P into L square, I'll take it to other side. Therefore, I have EA A1 L square is equal to PL square. Minus sign, when I take it to this side, it will become plus PL square. So both sides, this L square will be get cancelled. Therefore, my A1 will be equal to P divided by EA. My value of A1 is P divided by EA. Now, let us substitute this value of A2 and this value of A1 in equation number 4 to get the displacement. So that is my final step. What is the final step in the Rayleigh method? Fifth step, find displacement. Fifth step is find the displacement. Therefore, my U1 will be equal to, it is A1 into L plus A2 into L square. This is my U1 expression, correct? No, I written here. So A1 into L plus A2 into L square. So I written U1 into A1 into L plus A2 into L square. So let us substitute the value of A1. The value of A1 is P divided by EA into L. plus the value of A2 is 0, 0 multiplied anything, it will become 0. Therefore, my U1 will be PL divided by AE. The same equation I obtained, PL divided by AE. What is the expression when a bar is subjected to the force at the free end? So, using mechanics of material also, I got the same equation, PL divided by AE, correct? No, here. The extension in the bar is given by PL divided by AE. Now, using this Rayleigh-Ritz method also, I am getting the value as PL divided by AE. Okay, now this is the displacement which is there at the free end. Now, as I have one more equation, I ask you to get, that is displacement at any random distance. What is that equation? It is A1 into x plus A2 into x square. This is the expression I have written here. At any random distance, expression is A1 into x plus A2 into x square. So same thing here. Only I need to substitute the value of A1 and A2. So A1 is P divided by EA into x. This x as it is, plus this term is 0 because A2 is 0. Therefore, displacement at any random distance is given by P into x divided by EA. That means when I substitute that value of x, if I substitute at the extreme end, it will become PL divided by E. When x is equal to L, it is PL divided by E. When x is equal to 0, my U is equal to 0. When there is no distance, when x is equal to 0, when I substitute x is equal to 0, this is entire term is 0, 0 divided by anything, it will become 0. So my displacement is 0 when x is equal to 0. Is it true? No. Why it is true? Because it is fixed end.
Okay, guys, the remaining problems we will continue in the next class. Please comment, share, and subscribe the channel. Thank you.